Jai Hind everyone. Welcome to the class of optical communication. In this lecture, we will discuss basically numerical problems on fiber modes and dispersion. So as discussed, the main contents for this lecture will be, in this lecture basically we will discuss how we can solve some numerical problems which are related to calculation of fiber modes, attenuation in the fiber, that is attenuation or losses in the fiber, and different type of attenuation and dispersion mechanisms available in the optical fiber communication. The dispersion problems will also include the problem from the material dispersion, that is chromatic dispersion or intramodal dispersion, and the intermodal dispersion, and finally in one numerical we will also calculate the total dispersion, that is combined effect of both intermodal and intramodal dispersions, etc. So let's consider the first numerical problem for this lecture. So the first question is, basically we are having a multi-mode step index fiber. That means we are given with multi-mode step index fiber, where the core diameter is 80 micrometer. That means we are given with diameter or 2A as 80 micrometer. That means radius is 40 micrometer. Then we are given with relative refractive index difference as 1.5%. So we are given with delta as 1.5%, that is 1.5 by 100, that is 0.015. Then we are given with the core refractive index, that is we are given with N1 as 1.48. Then what we have to calculate is, we have to compute is normalized frequency for the fiber. The normalized frequency is basically V number, is also known as the normalized frequency. And then we have to calculate, we have to compute the number of guided modes. So number of guided modes, as this is the case of multi-mode step index, so the number of guided modes will be MS. So these two we have to compute. So first of all we are calculating the normalized frequency or V number. We know that the formula for V number is V equal to 2 pi by lambda A N1 into 2 delta's power 1 by 2. So using this formula we can calculate the normalized frequency or V number. So in this equation we are given with operating wavelength lambda as this one 0.85 micrometer. So we are given with 0.85 micrometer. Radius of fiber we have calculated, it is given as 40 micrometer. Then N1 it is already given as 1.48. Then we are given with delta 1.5%. So that means all the values for the required parameters are given in the numerical. So using this formula we can calculate the V number. So V number will be nearly equal to 2 pi by lambda A N1 2 delta's power 1 by 2. So putting these values in this formula we will calculate as V number as 75.8. And then we need to calculate the number of guided mode, because this is the case of multi-mode step index. That means we have to calculate how many multiple modes are existing or propagating in the step index fiber. So as this is the case of step index fiber, so the delta is not considered, the profile, the alpha parameter is not considered here, because alpha is considered in the case of graded index fiber. So simply we will calculate the number of multiple mode will be nearly equal to V square by 2. So V we have already calculated as 75.8. 8. So putting this value, then we will calculate the number of modes propagating in the multi-mode step index fiber. So that means V number is approximately 76 and number of guided modes are nearly 3000. So let's say next numerical. This numerical is for basically the graded index fiber. That means we have to calculate the number of modes for the graded index fiber. So again in this numerical also we have to calculate the total number of modes. So in this case this is the graded index fiber, so it will be mg. And then we have mg equal to v square by 2 into alpha over alpha plus 2. This is the formula. So if we calculate, then we are given with graded index fiber, that means it is a multi-mode graded index fiber. Then we are given with parabolic refractive index profile. So it is a graded index fiber, so parabolic profile means alpha equal to 2. So this is the case of graded index fiber, so we have to consider the alpha parameter also here. Then we are given with diameter as 50 micrometer. So D equal to 50 micrometer is given, so A is 25 micrometer. Then numerical aperture is given, numerical aperture is 0.2. So before calculating the number of guided modes, we are already given with alpha equal to 2 is given here. So we will calculate the formula as v square by 2 into 2 by 4, that means v square by 4. So the number of modes existing in this multi-mode graded index fiber will be given by the formula v square by 4. So we will use the formula as v square by 4. Now again we will calculate the v number using the formula v equal to 2 pi by lambda as from the previous numerical a n1 2 delta power 1 by 2. Now this term can be written as, we know that this is numerical aperture. So we will use the formula as v equal to 2 pi by lambda a numerical aperture, because numerical aperture value equal to 0.2 is given in this case. So using this formula we can calculate the v number as 31.4, and using this formula the number of modes existing are 247. So from this we can see that the v number in the case of graded index fiber is slightly less, and so accordingly the number of modes propagating in the graded index fiber are also less as compared to the step index fiber. Another numerical is there. We have a graded index fiber with a parabolic index profile. Again we have graded index fiber, parabolic profile means alpha equal to 2 is here. We are given with refractive index at the core axis is 1.5, that means n1 equal to 1.5 is given. Then we are given with relative refractive index difference delta equal to 1%, that is 0.01. Then estimate the maximum possible core diameter, that means 2d we have to calculate, or we can say that diameter is to be calculated. So diameter is equal to 2a. So basically we will calculate the a and then we will double it to calculate the diameter, because the formula for V number is available in terms of a. So we will compute the a using the V number formula as discussed in the previous slide, and then we will calculate the diameter by doubling it, and which allows single mode operation, at a wavelength of 1.3. That means for the single mode operation, we know that when V becomes Vc, then lambda becomes lambda c. This is the case of single mode fiber. So in the case of single mode operation, V becomes Vc and lambda becomes lambda c. So in this case, lambda c is given here as 1.3 micrometer. And this is the case of graded index fiber. So in the case of graded index fiber, this Vc will be computed in terms of alpha. So it is given by Vc equal to 2.4 into 1 plus 2 by alpha power 1 by 2. So this is the formula for the case of graded index fiber, cutoff value for the graded index fiber. If this would have been the step index fiber, then simply Vc should have been equal to 2.4 or 2.405. So we will compute this value of cutoff value for the Vc as 2.4 into 1 plus 2 by alpha. Alpha is taken as 2 because parabolic profile is given here. So for the parabolic profile, alpha equal to 2 is given here. So using alpha equal to 2, we will calculate as Vc equal to 2.4 into under root 2. So in this way, we have calculated the Vc. Then simply we have to calculate the A. So we will use the formula of V equal to 2 pi by lambda A n1 into 2 delta power 1 by 2. So here when lambda becomes lambda c, V becomes Vc. So in this formula, we will use Vc equal to, as we have calculated this one, and putting all other parameters, we can calculate the value of A. A can be computed. So using this formula, we can compute the radius of the optical fiber core. So by putting these given values, we will get the radius of the optical fiber core as 3.3 micrometer for the case of single mode operation. So we have to calculate the maximum possible diameter. So diameter will be radius multiplied by 2. So it will be 6.6 micrometer, which is within the acceptable range of less than 10 micrometer. We have already studied that the diameter range for the case of single mode operation is generally less than 10 micrometer, or we can say that it is 2 to 10 micrometer. So for this fiber to behave as the single mode fiber, the diameter will be equal to this one, or we can take less than this value. This is the maximum possible diameter. Another numerical is there. So we have to calculate the cutoff wavelength for a step index fiber. Cutoff wavelength is lambda c. Okay. Cutoff wavelength is, it is the wavelength above which the fiber becomes single moded. That means for the fiber to operate as a single mode, we have to operate with this wavelength or above this wavelength. Okay. So when lambda becomes lambda c, then we have V becomes Vc. Okay, so this is the case of step index fiber. So in the case of step index fiber, we simply have Vc equal to 2.405. As this is the case of step index fiber, so here the alpha, that is profile of the fiber, is not considered. So the cutoff value will be directly given as 2.405. So when we have V equal to Vc, that is 2.405, in that case, if we calculate the lambda, that will become the cutoff wavelength, lambda c. So using the simple formula, V equal to 2 pi by lambda a n1 into 2 delta power 1 by 2. So simply we have to take lambda equal to lambda c and V becomes Vc. So take Vc as 2.405, lambda c we have to calculate, A is given as radius as 4.5, so it is already given as 4.5 micrometer. Then n1 is already given as 1.46 is given. Then we are given with delta is already given as 0.25%. So putting all these values, we can compute the value of this cutoff wavelength. So putting in this formula, if we compute, the cutoff wavelength comes out to be as 1.2 micrometer nearly, or we can say that 1214 nanometer. So for a fiber, or for this fiber to behave as a single mode fiber, we have to operate with wavelength this one or above this wavelength. Okay, so the fiber becomes single moded if we operate with this wavelength or above this wavelength. The next numerical problem, basically this numerical problem is related to attenuation. Okay, and we know that attenuation, also known as the loss. Basically, attenuation or loss is the reduction in the strength or power of the optical signal while propagating through the fiber. So basically what happens, in the fiber, there will be a power entering into the fiber and there will be a power at the output of the fiber. So this Pi is generally known as the input power and this is known as the P output power. And in the case of fiber, there will be losses or there is reduction in the strength of the signal. So this P out, PO will always be less than the P in. The difference between these two power is known as the attenuation or loss. So simply, as loss is also, or attenuation or loss is also represented like gain in the case of dB. So in the case of power and representing the attenuation or loss in terms of dB, the formula is given as signal attenuation or loss equal to 10 log Pi by P out. From this, we can also calculate the power ratio Pi by P output I as 10 raised to power loss in dB by 10. So we can also calculate this. So based upon this, we have this numerical. So what is given here as the mean optical power launched into an 8 kilometer length of the fiber. That means in this case we are given with length of the fiber as 8 kilometer. Okay. So Next we are given with as power launched as 120 microwatt. That means 120 microwatt is P in. This power is given, or P in or Pi is given as 120 microwatt. Then we are also given with as P out as 3 microwatt. So this is P out. Now we have to calculate the overall signal attenuation or loss in decibel through the fiber, assuming there are no splices or connectors. That means for connecting the fiber we are not using any additional splice or connector, so there will be no additional loss. Only the loss will be in the fiber, that will be corresponding to transmission loss or alpha factor. So the losses is given by, as discussed in the formula, we will use this formula. Loss or attenuation equal to 10 log Pi by P out. So putting in the formula simply, 10 log P input 120 microwatt and P output as this one. So this is the 16 dB attenuation or loss in the fiber. Then in the second part we have to calculate signal attenuation per kilometer. So this attenuation is for 8 kilometer length of the fiber. If we have to calculate the signal attenuation per kilometer, so simply we will divide this total attenuation or loss with this length of the optical fiber. So simply, and this attenuation coefficient, this signal attenuation per kilometer is known as the attenuation coefficient or loss coefficient alpha. This is the loss in dB per kilometer. So alpha or loss coefficient will be alpha equal to 16 dB divided by 8 kilometer. So alpha will be simply equal to 2 dB per kilometer. So this is the transmission loss factor, 2 dB per kilometer. So in the third case, this is the third case, overall signal attenuation for 10 kilometer optical link. Now the distance we will be using will be 10 kilometer. So length will be 10 kilometer. And in this case, using the same fiber, that means for same fiber means alpha will be same. So the transmission loss for this 10 kilometer length will be 2 into 10, that is 20 dB. So loss of 20 dB will be there in the fiber when we use the same fiber over a length of 10 kilometer. Plus in this case we are having splices at a 1 kilometer interval and loss because of splice is 1 dB. That means for the 10 kilometer we are using splices in between which are at a gap or interval of 1 kilometer. So for a 10 kilometer distance we will use splices only at in between. So in the starting and in the end there is no requirement of jointing, so there will be no requirement of splices. So over this 10 kilometer of distance, so splices are used here like this. So in this case, for a 10 kilometer distance, number of splices required will be 9. Okay. So the number of splices required will be 9 and loss corresponding to one splice is 1 dB. So loss because of splice will be 9 dB. Okay. So overall loss in this case will be, in the case of this C part, will be 20 dB because of transmission or length or distance and 9 dB because of splices present in the 10 kilometer distance at a interval of 1 kilometer each. So total loss will be 29 dB. Okay. So next D part is numerical input output power ratio. So for this case we have to calculate the numerical input output power ratio. That we have calculated. The loss because of distance 20 dB, loss because of splices 9 dB, total loss is 29 dB. So the loss power ratio coefficient is Pi by P out equal to 10 raised to power loss in dB divided by 10. So it is simply as 10 raised to power 29 by 10. So the ratio is approximately 795. Okay. So this is the power ratio. So the power that we are providing to the fiber input and the power that we are receiving at the output, the ratio between these two power is approximately 795, or we can say that the output power is 795 times less than the input power. That means in the fiber there is significant amount of attenuation or loss. One more numerical is a multi-mode graded index fiber is there. Multi-mode graded index fiber is there with a total pulse broadening of 0.1 microsecond. That means pulse broadening in terms of time that we have defined in theory as this is the dispersion. So this is pulse broadening or dispersion. So this pulse broadening is a measure of dispersion. Okay. Over a distance of 15 km. So we can see that T equal to given here as 0.1 microsecond and length of the fiber is given as 15 km. Okay. So we are to calculate as maximum possible bandwidth on the link assuming no symbol interference. So maximum bandwidth is given as beta equal 1 upon 2t or 2 tau. We can also take as tau, or in the case of Gaussian pulse we can take as B optimum or maximum as 0.2 over sigma or sigma s, RMS pulse broadening. If we take the RMS pulse broadening and pulse as Gaussian pulse, then the formula used will be this one. So simply optimum bandwidth will be 1 upon 2 tau. So 1 tau is given as 0.2 microsecond. It is 2 into tau. Tau is given as 0.1 microsecond. So simply we have to 1 upon 2 tau is 0.1 microsecond 10 raised to power minus 6. So simply this becomes as 5 megahertz. So this is the bandwidth. Then we have to calculate is pulse dispersion per unit length. So here the pulse dispersion is given as 0.1 microsecond and length is 15 km. So if we have to calculate per, we will divide this tau divided by this length of the fiber. So simply this is the tau dispersion and this is over a length of 15 km. So dispersion per unit length of the fiber will be, if we divide, 6.67 nanosecond per kilometer. Then we have to calculate the bandwidth into length product. We have studied that this bandwidth into length product in the case of fiber, that is bandwidth into length product of the fiber, is known as the information carrying capacity of the fiber, and this is bandwidth 5 megahertz and length of the fiber is 15 kilometer. So bandwidth into length product is 75 megahertz kilometer. So basically the information carrying capacity of this fiber is as 75 kilometer and megahertz kilometer. So that's all for this lecture. A few problems we can discuss in other class. Thank you. Jai Hind.